Hey everyone, in this video we will discuss the question from CSIR NET 7 2023. This is the question from linear algebra. Okay. So let's read the question quickly. They are given a 3 by 3 real matrix A whose characteristic polynomial Pt is divisible by t square. Okay. And this is the only information that they have given. Now they are saying that which of the following statement is true. The eigenspace of A for the eigenvalue 0 is two-dimensional. What does what does that mean? That means the geometric multiplicity for the eigenvalue 0 is 2. Okay. This is the option. Is it true or not? We have to check. Next option is all the eigenvalues are real. And third option is a cube equal to 0. And fourth option is A is diagonalizable. Okay. Now you pause and think this. Okay. Now, let me tell you. First of all, the information that is given in the question is A is a real matrix. This is important. Okay. The matrix is real. That means all the entity in the matrix should be real. And its characteristic polynomial is divisible by t square. What does that mean? That means its characteristic polynomial must be equal to of this form t square into some t minus a. Why I have written like this? T square they have given that the polynomial should be divisible by t square. The characteristic polynomial should be divisible by t square. So t square will be a factor and another factor must be in linear form. So I have written this in this form t minus a, and this a should belongs to r. That means this a should belongs to real number. Why I have written this, that this a belongs to real number? Can you think about this? Why this a is a real number? Why this is not a complex number? Can it be a complex number? In characteristic polynomial, if the matrix is real, this matrix is real, 3 by 3 real matrix, can it be that in the characteristic polynomial the factor can be an imaginary? Is it? If it is true, then why it should be? Give me an example. And if it is not true, then give me another example or give me the reason. So, if the matrix is real, you think about this matrix. Suppose this is 0, this is 1, this is minus 1, this is 0. So, if this is the matrix, suppose this is a matrix. Now, the linear factor of this, is it all real number like this? T minus a into suppose t minus b. It's the characteristic polynomial for this matrix is t minus a into t minus b. For example, then this a and b, are they real? No, they are not real. Okay, you think about this. But for this matrix, that this A is a 3 by 3 real matrix, the characteristic polynomial is divisible by t square, right? So it should be looks like this from t square into t minus a. And I have already claimed, and I that means I am claiming this A is real number. Why I am claiming this? Okay, just think about it. Why I am claiming this? Because if I am guessing the eigenvalue from this characteristic polynomial. You see, what will be the eigenvalue from this? The characteristic polynomial is t square into t minus a. So t square into t minus a equal to 0 will give you t square equal to 0 and t minus a equal to 0, right? So t square equal to 0, that implies t equal to 0, 0. So 0, 0 are the eigenvalues. Two eigenvalues are 0, 0, and the rest of the eigenvalues is a. Now, is it possible that this metric, this a, can be a complex number? If not, then why? Because you know the eigenvalue in the matrix, in the real matrix, right? This real is important. That they have given that this is real matrix. In real matrix, what happens? If there is an eigenvalue which is complex, then there should be another eigenvalue which is also complex, and it is the conjugate of these eigenvalues. Suppose a plus ib is an eigenvalue of a real matrix, then a minus ib must be an eigenvalue of this matrix. So that is the reason that this a cannot be a complex number, because if it is a complex number, then there should be another complex conjugate of this number. But we have already seen that two eigenvalue of this is 0, 0. So the rest of the eigenvalue must be a real number. So clearly from this, the option 2 is correct, that all the eigenvalues of A are real. but does not mean that all of the other options are wrong. But since it is a question from part B, then the only option that is right is option 2. But let's discard the other options, okay? 1, 3 and 4 by taking an example, okay? So for counter example, let us assume this matrix A, this zero matrix. Okay, if I why I am taking this zero matrix, because the characteristic polynomial of this matrix is what? This the characteristic polynomial is t cube, right? And t cube is divisible by t square. Divisible by t square, right? The characteristic polynomial is divisible by t square. Okay. Now we have to check the option 1, that is saying that the eigenspace of A for the eigenvalue 0 is two dimensional. That means the geometric multiplicity for this eigenvalue. What is the geometric multiplicity of this? Clearly you can see the nullity of A minus lambda I, if you see, that means nullity of A minus 0 I for the eigenvalue 0. This is this will be the same matrix, this 0 0 0 0 0 0 0 0 0. So what is the nullity of this? 1 2 3. 3 is the nullity of this matrix A minus 0 I, right? So the geometric multiplicity is 3. Why I am saying like this? Geometric multiplicity for any eigenvalue, suppose you have a matrix A, then the geometric multiplicity will give you by nullity of the matrix A minus lambda I. If you see the nullity of the matrix A minus lambda I, then this will give you the geometric multiplicity. So for this matrix A, 0 is the only eigenvalue. So I am checking that the of geometric multiplicity for the eigenvalue 0. So how I am checking? I am checking by the nullity of the matrix A minus 0 I. So this is 3. Now, so from there, I am getting the geometric multiplicity is 3. That means option 1 is wrong. Okay, so this is discarded. Now option 3, A cube is 0. Is it true? Let us take this matrix. A is equal to 0 1 0 0 0 0 0 0 1. So you can see this is a block time matrix, right? You can take this. So suppose this is a matrix B and this is D, this is 0, this is 0. So clearly from this, the characteristic polynomial is what? This is also t square into t minus a, right? The characteristic polynomial for this matrix is t square, and the characteristic polynomial for this matrix is t minus 1. Okay, so its characteristic polynomial is t square into t minus 1. So the eigenvalues are 0, 0 and 1. Okay, but for this matrix, if you do a square, then you will get this matrix at 0 0 0 0 0 0 0. That how I am taking this square. If you want to do it by a single step, you do the square of this matrix. Suppose this is the matrix B. Okay, since this is a block matrix and this is block diagonal matrix also. So if this is your A square will be given by, here this is given by B square. So this is actually equal to B square. This is equal to B square. Okay, and this is, say if this is D, then this is D square. Okay, so 0 1 0 0, the square of this is this 0 0 0 0, and this square is 1. So square is this. Now if you do the A cube, then also you will get this. But in option 3, it is saying that A cube must be 0. So this option is also wrong. Now option 4, is it diagonalizable? If I take the same example, this, that you see that the eigenvalues is 0 0 1 1. So the algebraic multiplicity of 0 is 2. If the geometric multiplicity of 0 is 2, then this matrix will be diagonalizable. But if I check the geometric multiplicity for the eigenvalue 0, then I will check the nullity of the eigenvalues, nullity of the matrix A minus 0 I. What will be the nullity of this? Clearly you will see that nullity will be given by this row only, right? That means nullity is 1. What is the nullity of this matrix? 1, right? So since the nullity of this matrix is 1, that means geometric multiplicity for the eigenvalue 0 is 1. But the algebraic multiplicity is 2. That means algebraic multiplicity is not equal to geometric multiplicity for this eigenvalue. So this matrix is not diagonalizable. Hence, option 4 is also wrong. So the only correct option for this question is option 2.